All right, so I want to talk a little about counting problems or combinatorics. I'm going to focus on uh, some of the basic ways we categorize problems, but really we don't categorize problems themselves, we categorize parts of problems. Usually a problem involves more than one uh, type of problem that kind of gets put together with another type of problem. But sometimes you can do a problem with just one method, and that's generally easier. So the general things you want to look for are things you're going to count where you are either arranging things or you're going to be just counting how many ways you can choose a sample out of a set of things. When you're arranging things, you may have objects, physical objects like blocks with numbers or letters on them, and you want to arrange those blocks. So arranging two blocks with the same letter is a different arrangement. But arranging letters that you're allowed to use as many times as you want from an alphabet means you're not actually arranging the objects themselves, but two letters are the same, so if they appear in two different places, you have to account for that. So first thing to think about is a factorial. A factorial is simple. It's just this number, n factorial, is just counts the number of ways I can have n objects put into different orders or arrangements. The idea is you have n choices for the first object, and then after you put that object in the first position, you only have n minus 1 choices for the next, and then n minus 2 for the next, and so on. However, if you're making strings of letters from an alphabet, you can repeat letters all you want. So when we construct a string of, say, k letters out of an alphabet consisting of n symbols or n letters, then the number of those different words or strings is just n to the k, because you have n choices for the first letter, and then you're allowed to repeat for the second, and you're allowed to repeat for the third if necessary. So this first bullet point here is really just referring to order counting without replacement, meaning after you place something, it's no longer available to be put in another place. And the second type is with replacement. You can always repeat symbols or letters. The other type of counting that's fundamental is counting how many ways you can just grab a sample of a certain size out of a set of objects. And that's what binomial coefficients are for. We read this as n choose k, given by the formula here to the right. And it's just counting how many ways I can choose a different sample of k objects from a set of n objects. Here, order doesn't have anything to do with it. It's just the group that you're counting. So if you grab a group of objects, they're just all sitting in front of you. There's no order to them. Changing any one of the objects with a different object you didn't pick gives you a different sample. So let's consider arrangements first. In this first video, we'll focus on problems with arrangements of letters. So let's consider our 26-letter English alphabet. So there's 26 to the 5th 5-letter long strings that we can form using the letters of the English alphabet. So then the question is, how many 5-letter long strings contain 4 distinct letters? What we want to do is think of a process, step-by-step process of how we would actually go about constructing a specific string to have this property. And then we basically count how many ways each step could have been done, but in our mind we're focusing on actually constructing maybe one particular example. So the first step could be we need to choose 4 distinct letters from our alphabet that we're going to use to create this kind of string. After we've chosen those 4, we then have to choose one of those 4 to be the one letter that's going to appear twice. Because if we only have 4 letters and there's 5 letters in the string, one of them is going to be repeated. After we've made that choice, then we're going to choose where to put that letter that's appearing twice. Since there are 5 locations in our 5-letter long string, we have to choose 2 of those 5 locations. Or at least there's 5 choose 2 ways we could choose to place those 2 letters that are the same. Once we choose where to put those letters, the other letters have to be placed in the other 3 locations, but they can be placed in different orders. So we have to count how many ways we can arrange those remaining 3 distinct letters in different orders. So that's why we get 26 choose 4 for choosing 4 letters to use, times 4 choose 1, choosing one of those 4 letters to be the one that's going to be repeated in the word, and then choosing 2 of the 5 locations in our string to put those repeated letters, and then times 3 factorial ways of arranging the other 3 letters in different orders to create a different string. Next, how many 5-letter long strings contain 4 distinct letters with repeated letters appearing consecutively? So now what I've described here is actually a subset of the set of strings we just counted. So this is going to be a smaller number, because now the 2 letters that are the same have to appear in the string next to each other. So again, we break it down into a process, which is very similar. We choose 4 distinct letters from the alphabet. We choose one of those to be the letter appearing twice. But now we have to place those 2 repeated letters next to each other in the string. So there's only one of 4 places we can put those. We can put them as first, second, second, third, third, fourth, or fourth, fifth. Once we place those, again, we have to arrange the other 3 letters in different orders, because they're distinct letters, so all arrangements of them have to be accounted for. So the only difference in the answer here is the third number. Instead of being 5 choose 2, it's 4 choose 1. So this gives us a smaller answer. All right, let's look at another problem. How many 5-letter long strings contain only the letters A and B and contain at least 2 of each of these letters? So what does that mean? That means there's either going to be 2 A's and 3 B's, or there's going to be 2 B's and 3 A's. So this is a problem where we can do it directly with the multiplication principle by creating a process. So first, 2 choose 1 is just choosing one of those 2 letters, A or B, to be the one that's going to appear only twice. Once we make that choice, there are 2 locations out of the 5 where we can put those. And once we choose that, the other 3 letters, whichever they are automatically placed. We don't have a choice left. Next, how many 5-letter long strings contain distinct letters appearing in alphabetical order? Now the answer here might surprise you, but if you think about it, it's pretty straightforward. We're just choosing 5 distinct letters. Because once we choose 5 distinct letters, there's only one way to put them in alphabetical order. So that's the answer. Now, how many 5-letter strings contain at least 3 Z's? Now this is a case where we want to break the problem up into mutually exclusive sub-problems, which are easier to do with the multiplication principle. So we look at specific cases of having exactly 3 Z's, exactly 4 Z's, exactly 5 Z's. Also, this problem doesn't say we can't repeat the letters. So if we're going to have 3 Z's, we have to choose 3 of the 5 locations to put those Z's. Once we place those, we have 25 choices of letters, because we can't choose a Z anymore. We can choose anything but Z for each of the remaining 2 places. Then we add this because the case of 3 Z's and 4 Z's are mutually exclusive. So now I'm going to count how many ways I have 4 Z's. I choose 4 of the 5 locations to place the Z's, and then I just choose a non-Z letter to fill in the last place. And then how many ways can I have 5 Z's? Well, there's only one. I have 5 Z's, and that's it. What we're really saying is choose 5 of 5 locations, which is 1. So adding those 3 mutually exclusive pieces, or partition pieces, of our event, at least 3 Z's, allows us to add up all of those. Now, to compute the probability of any of these events that we've discussed, all you'd have to do is take these numbers and divide them by 26 to the fifth, or the total number of 5-letter long strings. Now let's look at before we move on to some other examples, let's explain a little bit the binomial coefficients and how they kind of relate to these string problems, even though they're not used when there's order in a problem. So let's consider a smaller alphabet, just so we can see things a little bit easier. So we have an alphabet of 4 letters, A, B, C, and D. There are 4 factorial, or 24, different strings with different letters. So 4 different letters in them. I've listed them here. Out of those 24 words or strings that we've made, we can group them together based on the fact if they have the same exact first letter and same exact second letter. In other words, that's the same as, this grouping is the same as just saying how many 2-letter words can we make with distinct 2 letters out of this 4-letter alphabet. And that's 12. So you can see we've grouped the words ABCD and ABDC because they have the same first and second letter. That corresponds directly to the word AB. In other words, the label AB can be used to label this set. And each of these other sets has another label based on the first letter and second letter of the words in each group. Similarly, there are 6 groups of strings where the first 2 letters are the same as a set, meaning the first 2 letters are the same, but the order in which they appear doesn't matter. So now we can see, for example, AB is always appearing in the first 2 letters of these 4 words, so they're getting grouped together, counting them as one set of letters, AB, for the first 2 letters. So again, all we have here at the bottom is the total number of subsets of 2 letters from our alphabet of 4 letters, which is just 4 choose 2.